Hello and welcome to another episode of Echo Live. My name is Alyssa and I'm a scientist here at the Michigan Science Center. Now today we're here to talk about one of my favorite topics of all time. And it sounds pretty simple, but we're here to talk about the states of matter. What makes up the world around us? Now you probably have a lot of really good ideas about what those states of matter are. But first, let's talk a little bit about the history around this theory. What did people in ancient times think things were made out of? So we're going to start our discussion today with a person named Empedocles. Give me one sec, let me get my screen all ready to go here. So this is a picture of Empedocles. I think it's a pretty funny picture, which is why I wanted to start with it. So Empedocles was a philosopher and natural scientist who lived about 2,500 years ago. And Empedocles was born on an island called Sicily. At that time, it was associated with the Greek Empire. And he was educated in a group of people called the Pythagoreans. The Pythagoreans were very famous for believing that numbers ruled everything, that numbers were the most important thing. And he was a pretty well-established scientist in his own right. He actually got a lot of things correct. He had a lot of really good guesses about things in our natural world today. So for instance, he guessed that the speed of light is constant. We know that that's true. He also guessed that something called mass is conserved, meaning whatever you go into your chemical reaction with, you're gonna come out with basically about that amount of stuff. Now, he also got the idea of natural selection sort of right too. He guessed that animals and things that are alive would become more or less fit based on how their bodies worked. Now, he got all those things right, but he also got some of those things wrong. So for instance, he had really, really distinct ideas about, about what things are made out of. So Empedocles thought that everything was made out of one of four things: fire, air, earth, or water. Now, this might remind you of something familiar, something you might know about. This reminds me of Avatar: The Last Airbender whenever I like to hear about it. But it's really what Empedocles thought. He's not the first person to think something like this. Scientists before him thought that it was possible that everything was made out of water or everything was made out of air. But he sort of combined all of those things together and said, no, everything's either made out of water, air, earth, or fire. And some things have more than others. So for instance, a bunny rabbit has more fire than, for instance, a rock, which is mostly made of earth. And his idea really caught on. In fact, our guy right here in the middle, Aristotle, one of the most important scientists or philosophers of his time, believed in the elemental theory. He believed that yes, everything is made out of fire, earth, air, or water, but the reason it's different is because everything has a different form. A bunny has a different form than a rock. And that's why even though they're made out of the same things, they're a little bit different, right? Now, one of my favorite people too to talk about whenever we're talking about the history of the states of matter is a guy named Democritus. Democritus was born in 460, and he was most famous for coining the term atomos, or the smallest indivisible particle. Now, this might remind you of something called atoms. And atoms are exactly that. At his time, people thought they were the smallest indivisible particle. Okay, so we've got Democritus, who believed in atoms, the smallest indivisible particle, which should ring some bells for you. We've got Aristotle, who probably believed in the elemental theory that everything was made out of fire, earth, air, and water. And honestly, for about 2,000 years, that's basically what everyone believed. Everyone thought, Aristotle, that guy is so smart, he must have it right. Everything's probably made of fire, earth, air, and water. Now, it wasn't until only about 300 to 400 years ago, during the scientific revolution, that people thought, you know what, maybe there's something else going on. And in fact, this other guy on our screen, John Dalton, was known as a huge pioneer of chemistry. John Dalton said, you know what, I bet everything is made out of these tiny, tiny particles. He called them atoms, a lot like Democritus, born 2,000 years before him. And he thought, yeah, so there's these really tiny things, And you know what? If you put those really tiny things together, they make new things. And that's a lot more like what we have now. And actually, by about 1870, scientists were pretty much agreed as to the fact that everything is made of atoms, and those atoms come together in different configurations at different angles, at different temperatures, and make the matter that we know of today. So we know that everything is made of atoms, right? It's those tiny indivisible particles. They're not quite so indivisible as they thought back then. They are, of course, made of subatomic particles like protons, electrons, and neutrons. But those atoms come together and they form something called molecules. Molecules are really they're the way that we understand matter. They're the easy way I understand matter, at least. So, for instance, let's take this water. Got water right here. And we have, if I took this cup of water and I poured it into a cup half that size, I would have half the amount of water. If I took that littler cup and I poured it into an even smaller cup, I would have even less water. And in fact, I could keep on doing this for a very long time, and eventually I would only have just the tiniest bit of water, just one molecule of water. And that's what a molecule is. It's the smallest unit of that kind of thing. So we've got water, easy peasy, but that molecule of water is made of atoms. And those atoms, I'm going to show you another picture of them over here. Those atoms is one oxygen atom and two hydrogen atoms. That's why we call it H2O. We've got two hydrogen and one oxygen. All those atoms come together and they make a molecule. Now that we understand molecules, we'll be able to understand a little bit better about the states of matter. So, you guys have probably heard of the states of matter before. We talk about them a lot here at the Science Center. One state of matter that I like to start with is I like to think about a solid. Solids are the first state of matter we're going to talk about. Solids are hard. Whenever I ask people to describe a solid, they say hard, or you can't bend it, or sometimes they say cold or hot. And I love that people are thinking about the behavior of matter, and even the temperature of matter is very important. So the way I like to think about a solid, whenever I'm trying to figure out whether something's a solid or a liquid, is I like to think about what it does when I put it in a new container. For instance, I have a small remote right here. This remote, you guys would know intuitively, of course, is a solid. And one of the ways we can test that theory is if we put it in a new container. Now, I don't have a container that fits this remote, unfortunately. We'll do another experiment in a moment where we're going to put this to theory. But if I put this in a new container, say a big bucket, this remote wouldn't become bucket shaped. It would stay remote shaped, and that's how we know it's a solid. Now let's talk about liquids. If I've got, so for instance, say I've got a block of ice. Now, before the block of ice melts, if I put it in a new container, say a cup with no liquid in it, it would stay ice shaped. But what happens as that water continues to sit in that cup, probably at room temperature? Well, we're adding thermal energy to that ice, and in fact, that ice starts to melt. Now, whenever that ice melts, it's going through a state change. It is turning into a liquid. So, the way I like to define liquids are liquids change shape when you put them in a new container. Take, for instance, this water right here. If I put this water in, if I poured it in, say, a big bucket, it wouldn't stay the small cylinder shape. No, it would cover the bottom of the bucket, it would flow, and you could tell that it was a liquid. So we've got solids and we've got liquids. The next one we're going to talk about is gas. Now, people don't often think about it like this, but you can actually describe gas exactly the way we've described these. Their behavior when you put them in a new container. So say, for instance, I've got this water and I have it on a pot on my stove, and I turn that stove all the way up. And I'm adding a lot of thermal energy to that stove, to that pot of water. Eventually, that water is going to evaporate. It's going to turn to steam, some people would say. It's going to go from liquid to gas. Now, the way we can tell it's a gas is because that vapor, that water vapor or that steam, it lifts on up out of the pot and it fills its new container being the room. That's what gases do. Gases don't just flow around the bottom of the container. Instead, gases fill the entire container. They try to expand as much as possible. And in fact, I have got a picture of that right over here. Give me 1 second. Okay. See if we can get over to my next slide. There we go. So we see that we have a solid first. Those molecules are very orderly. They're not going to change when you put them in a new container, right? They're going to stay that shape. And then we've got that liquid. See how that liquid, those molecules in that picture are just, they're moving around. They can flow around each other a little bit. And then we've got the gas. Now that gas, it doesn't stay on the bottom of the new container, does it? No, it expands and it goes all over the room. Okay, but you'll notice that there is, of course, a fourth state of matter on my slide here. That fourth state of matter is something we talk a lot about here at the Michigan Science Center, and that, of course, is plasma. Now, we don't find plasma very often here on Earth, but it is, in fact, the most abundant state of matter in the universe. We find plasma when gas has been ionized or when electricity is flowing through gas. And you'll see in the slide that there are little positives and negatives, and that sort of denotes the fact that plasma is energized by electricity. But where do we see that on Earth? We see it on Earth in a couple places. The most notable place we see plasma is actually in lightning. Lightning is made of plasma because lightning exists because of a potential difference between the Earth and the sky above it. There is a potential difference, so the electrons travel, it ionizes the air and creates plasma. We also see it whenever we use static electricity, which is also what lightning is. You guys have probably rubbed your feet on the carpet on like a really dry day and maybe like poked your brother on the nose, maybe created a little shock. That's static electricity, and you just created a teeny tiny bit of plasma. But I did tell you that plasma was one of the most abundant states of matter in the universe. And in fact, it is what most of our stars are made of. Plasma is incredibly important. Now, we've got those three states of matter, right? But there are actually some really weird states of matter that I want to talk to you guys about today. Before we get to that, I just have a small demonstration. This is a really fun demonstration that I like to do that sort of illustrates all the different types of states of matter other than plasma, of course. So I've got this stuff right here. This is called Alka-Seltzer. You guys might have known about it. Your parents might know about it. It is a medicine. You can buy it over the counter. And it has a couple different ingredients, one of which is aspirin, which helps with the pain relief part. That's what might get rid of your headache. But it's also got two other ingredients that I want to tell you guys about. The first ingredient is sodium bicarbonate. Sodium bicarbonate is most well known for being called baking soda. You might have that stuff in your kitchen. It has another ingredient though, and that's called citric acid. So we've got baking soda and citric acid. And the cool thing about baking soda and citric acid is that when they come together, a chemical reaction takes place. Now, probably doesn't look much like a chemical reaction is taking place right now. In fact, there's really not much happening. That's because both the citric acid and the sodium bicarbonate are in solid form. This is obviously a solid, right? If I put it in a new container, say for instance, this Erlenmeyer flask, it doesn't change shape. It's still Alka-Seltzer shape. So what I'm going to do is I'm going to add some liquid, some water. And this liquid water is going to allow the baking soda molecules to meet the citric acid molecules. And when those things can finally come together and they're not stuck in their solid shape, they can flow around each other, then we'll actually be able to see the reaction take place. Now, I'm going to actually see if I can put a balloon over the top of my Erlenmeyer flask and see if we can capture some of the substance, the state of matter created. You guys ready to watch? Okay. I'll pour some water in. And actually, I'm going to put a little bit more of the Alka-Seltzer in, and we're going to see if we can capture some of this stuff being created. Let's see. And you'll see very quickly that in fact, my balloon is filling. And what's it filling with? Well, we know that solids don't change shape when we put them in a new container. We know that liquids, although do take the shape of a new container, they don't take the shape of the entire thing. They stay at the bottom, they obey gravity, right? What we see actually is that there's a gas being created inside of this balloon. And that gas is called carbon dioxide. Actually, the gas is being created down at the bottom, but the gas is traveling up because it's filling its container, and now the balloon is part of its container. So that gas is carbon dioxide, and we have trapped it in our balloon right here. I like this experiment because it really illustrates all three of the states of matter most abundantly found on Earth. We have the solids, the Alka-Seltzer, we have the liquid water, and the gas in the balloon. Okay, I'm gonna see if I can take it off now. Okay, I'm gonna let it go. And there it goes. So those are our three most common states of matter: solids, liquids, and gases. And of course, we have plasma. Next, what we're going to do is talk just a little bit about two of my favorite facts about states of matter. Because when I was a kid, I learned that there are solids, liquids, and gases, and sometimes plasma. But I've done some research, and I've got some pretty cool stuff to share with you guys. Because in fact, solids, liquids, and gases aren't the only types of states of matter. In fact, something that's as common as glass is considered an irregular state of matter. It's a state of matter called an amorphous solid. So let's talk a bit more about what that means. You see, I've got a picture on the screen of some stained glass. I thought that was really pretty. That's at a cathedral in Dallas, Texas. And it's got a ton of glass, right? So to understand how glass is different, you kind of have to understand what a crystal is. And crystals, essentially, you guys have probably heard about crystals, but in this case, when we use the word crystal, what we mean is that it's a solid that has a structure that repeats itself. So you can see the crystalline structure on the screen. You can see that those sort of hexagon shapes are very orderly. They're all in a row. That oxygen and silicone, which is what glass is made out of, is ordered really nicely, right? It's in this like beautiful pattern. Now, you'll see right next to it though, where it says amorphous solid, that's actually what glass looks like on a molecular level. Glass is not a liquid, or sorry, gas is not a crystal, because crystals are orderly, where glass is not. Its molecules are kind of funky shaped. They are at sort of strange angles, and those strange angles have the ability to be moved. They're a little bit malleable. And although glass doesn't really move that fast, it doesn't move fast at all, right? It technically is a amorphous solid, meaning that it is more malleable. Those angles can change, and theoretically, they might be able to flow. That's why glass blowers find it so easy to get that glass hot, turn it into a liquid, and shape it. Now, one of the things I think is really fascinating about glass not being a crystalline structure, or the fact that it's an amorphous solid, more like a liquid, is that when I was a kid, I learned that in really old churches, that the glass that had been there for thousands and thousands of years might be thicker on the bottom because gravity is actually very slowly pulling those amorphous solid molecules down. And because it's not in a crystalline structure, it's a little bit easier for them to pull them down. So those windows are thicker on the bottom. It's one of my favorite stories. I don't know if it's true. Unfortunately, I do have to do some more research, but I think it's fascinating to think about something like glass that we think of as solid as having liquid-like properties. Now, that's one of my favorite things to talk about whenever it comes to weird states of matter. The other one is this stuff on the screen. Now, this is called liquid crystals. Sounds a little weird, but you guys have probably used liquid crystals before. Liquid crystals are actually what mood rings are made out of. Now, you might have been told that mood rings were changing colors based on your mood, right? You find them sometimes, they're on rings, or you can find a necklace, and they'll say, oh, if it turns blue, then you're happy. If it turns red, then you're angry. Well, I have some unfortunate news for everyone. They're not reading your mood. In fact, liquid crystals, which is what mood rings are made out of, change based on the temperature. So inside of a liquid crystal sheet, like a small mood ring, you'll see that if we could get down to a molecular level, you would see something a lot like my picture here on the right. In its coldest form, those crystals are aligned, that crystalline structure, very uniform. But as you keep on adding heat, those crystals sort of get unwound. They start getting a little bit more flowy, start moving in some weird ways, a little bit more like a liquid. So just like how glass was a solid that, glass was a solid that might move like a liquid sometimes, maybe very slowly. Liquid crystals are a liquid that whenever they're very cold, they act like a solid. It's one of my favorite examples. Okay, friends, I have one last really cool thing to show you guys. One of my favorite examples of a weird state of matter. Now, I know Anna here on Echo Live and a lot of you at home have probably made slime before. Slime is one of my favorite things to make. Slime happens whenever we mix something like a liquid plastic with borax. And that liquid plastic and that borax, it comes together and it makes a really weird substance. I've actually got some of it right here. I didn't want to take the time to make it on air today, so I made it beforehand. And I've got it right here. I dyed mine orange. And those of you that have played with slime before, you might recognize what I'm doing. I'm just simply stretching it. But the weird thing about slime is that slime changes properties based on a change in one variable. Now we think of with liquid crystals, right? That variable was temperature. That's the thing that we were changing. With glass, it's also temperature. You can apply a little bit of heat to that, turn it more into a liquid. But the variable I want to talk to you about now is pressure. Because in fact, slime reacts differently under different types of pressure. So for instance, if I have my slime in a ball, and I have like really tough slime today. This is not very sticky or stretchy slime. If I use this slime and I pull it apart really quickly, 1, 2, 3, it crumbles. I always like to say it kind of crumbles like I pulled apart a muffin, right? But if I tear my slime apart really slowly, it's not crumbling and it's definitely not like a muffin, at least not a muffin that I would want to eat. And that's because I'm not putting as much pressure on it. So I'm allowing things to stretch. And the reason this happens is because slime is a different kind of state of matter than solids, liquids, and gases. It's a very special kind of liquid called a non-Newtonian fluid. Non-Newtonian fluids are basically liquids that don't act like liquids. In this case, whenever you put pressure on it, it turns into a solid. But whenever there's less pressure on it, you can stretch it really slowly and it acts more like a liquid. Now, why does this happen? Well, I'll leave you with this today. It happens because of the chemistry, those chemical bonds. You see, that borax that you add whenever you make slime, when you add it to glue, it creates a really weak bond. That really weak bond, I like to think about it sort of like a spring. Whenever there's pressure on that bond, it collapses and it gets really tight and it's really hard to move. It's more like a solid. That's why I feel like this. The slime is more of a solid. But if I allow that bond to sort of relax and stretch out, again, sort of like a slinky, then it acts more like a liquid and it's able to flow. Okay, guys, that's all I have for you today. Thank you so much for joining me here on this last episode of Echo Live. Join one of us next week. We'll keep on going with these Echo Lives at 2:30 on Wednesdays. And we'll see you again very soon. Thank you so much. Bye.